CST video studying. Today, right now, we're looking at similarity, congruence, and surface area. Let's do it. Use the proof to answer the question below. What reason can be used to prove that the triangles are congruent? Okay, well, let's follow what it's giving and let's start marking our triangle here. It says D is the midpoint of AC. So AB is congruent to BC. Alright, well, it's saying that this long side is congruent to this long side. And then AD is congruent to CD, so that means this side here is congruent to this side here. And then the last one is BD is congruent to itself, so this inside piece is congruent to itself. Well, it looks like they're using three sides for the proof. That means that we would be using the side, side, side theorem, which is D. Which triangles must be similar? Well, that's kind of interesting. Two obtuse triangles. Well, I know that's not true. How do I know it's not true? Because I can make it so they're not. This is obtuse, and so is this, and they are not similar. Two scaling triangles with congruent bases. So in other words, the sides are not the same. The other two sides are not the same, but it's got one side the same. So if I have this piece here, and I'm going to copy and paste it, make two of them, make one of them kind of see-through. I'm going to move the other sides around a little bit. So that would be scaling, and this one would also be scaling. They have a congruent base, but they're clearly not the same triangle. So both A and B are out. Two right triangles? No way. I mean, 45, 45 and 30, 60, 90. Those are not similar because all three angles have to be the same. Then it must be D. I'm not even going to read it or try to explain it, but I know the other three are wrong. Two isosceles triangles with congruent vertex angles. Well, even if we couldn't explain that, we know it's right because the other three have to be wrong. Let's go ahead and keep on moving. I'm not saying that I can't explain it, just in the interest of time. You don't always have to. Which of the following facts would be sufficient to prove the triangles ABC and DBE are similar? So if we're trying to prove that things are similar, we need some type of angle relationship. So your options are usually angle, side, angle, angle, side, or angle, angle, angle. And with the side, angle, and angle, side, angle, you also have to prove that that other side is proportional. Alright, well, let's see what we got going on here. What would really help us? CE and BE are congruent. Would that help me? It could, but not as much as you would think. If I know that AC and DE are parallel, though, that helps me a lot. If these two lines are parallel, I get all kinds of congruent angles that are corresponding. For example, angle CAD and EDB, the two that I just marked, those would be the same measure. And so would these other two. And that gives me angle, angle. In fact, when you prove this, you don't need all three angles, you just need two. Why? Because the third one is kind of by default. As long as you prove the first two, the third one's always going to work out as well. Would anything else have helped me out? A and B being congruent, that doesn't really help me. ACE being a right angle, even if that was a right angle, what if DEB was not? What I'm really looking for is those two lines to be parallel. Alright, let's look for the next one. It's a little bigger. In ABC and XYZ are two triangles such that AB over XY equals BC over YZ. Which of the following would be sufficient to prove the angles of the triangles are similar? Oh man, so we got proportional sides going on here. So let's see how this would relate to each other. Let's go ahead and draw ourselves two triangles. Well, there's one, and here's one that's going to be the same but bigger. Actually, you know what? I know how to do that without having to Yes. I'm going to take this one, copy and paste it. Now we're going to make it bigger but proportional. Okay. So we're going to label these pieces A, B, C. Then this one is going to be X, Y, Z. I know that AB over XY is proportional, and BC over YZ. So that's kind of this side and this side is proportional to this side and this side. And for me to use a side angle side relationship between them, because it's either side, angle, or angle, angle. The side needs to be or the angle needs to be in between those two sides. So then what I'm looking for, actually this angle, why am I even saying that? It's really just these two here. Or side, if all three sides have the same proportions. That means we're looking at this angle B and this angle Y. Because it's got to be the angle between those two sides. If it was the other angles, that doesn't really matter then, the proportions of those sides. This third angles, A and C, the second and third angles, those don't really help me. So B and Y would have been the two that I'm looking for. Why? Because side angle side is one of the proportional relationships I can use. Next one. All these are a little bit small. Keep liking them a little bit bigger, a little bit easier to read. Which of the following best describes the triangles below? Okay, both similar and congruent. Well, I know that if that's 60 degrees, this is 30. And if I know that's 30 degrees, this is 60. How do I know? Because they're right triangles. So I know that they're at least similar, because the angles are all the same. Now, because I have one side the same, that means that the ratio, the proportional relationship is just 1 to 1. So it means they're also congruent, because whatever this side is, the ratio I would multiply to get the other one is just times 1. So that means for this bottom piece, I'm going to multiply by 1. And then for the height, I'm also going to multiply by 1. That similarity ratio is 1 to 1. So they're both similar and congruent. They are similar, but not, they are congruent. It's not that they're not congruent. And you can't be congruent but not similar. That's just stupid. That's not even possible. And they're definitely similar because they have tons of angles. All the same. Which of the following statements must be true if these two are similar? That's what this little symbol right here means. This little symbol means similar. The two triangles must be scaling. I don't think so. The two triangles must have exactly one acute angle. I don't even think that's possible, because if you have two obtuse angles, then you wouldn't have two triangles. So that one's out too. You gotta, because if I have an obtuse angle that's greater than 90 degrees, the two other ones together have to be less than 90 degrees, so they'd both be acute. At least one of the sides of the two triangles must be parallel. No. Because I can rotate one and it's still similar. It doesn't matter the orientation. So that one's out too. The answer must be D. But this is very true. The corresponding sides of the two triangles are proportional. Similarity implies a proportional relationship. In other words, you multiply by the same ratio to get from one triangle to the other. Which method listed below could not be used to prove that two triangles are congruent? Prove all three sets of corresponding sides are congruent? That would be side, side, side. Prove all three sets of corresponding angles are congruent? That would be angle, angle, angle. Prove that two sides and an included angle of one triangle are congruent to two sides and included angle of the other triangle. That would be side, angle, side. Prove that two angles and included sides, so that's angle, side, angle. So what it's asking us is between these four theorems here, one of these would not work to prove congruent. Well, that would be angle, 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 because I can have two triangles that are different sizes but have congruent angles. But the other three are all types of congruent relationships. Number 21. In the figure below, it says that AC is congruent to DF. I'm going to go ahead and mark that. And angle A is congruent to angle D. Which additional information would be enough to prove that the two are congruent? Let's see. I would hope that we're looking for this third side here, because side-side angle is that classic ambiguous case where we don't know. It might be congruent, but it might be not. So we're not going to look for that one. Instead, we have a side and an angle. We have two choices. We could either have angle side angle or side angle side. So it looks like we need to add a third side here. That side then would be this AB and DE. So we need AB is congruent to DE. All right, that would be A. And the other three we're not even going to look at because we found our right answer. Number 21. Keep on moving here. Given that they intersect at point E, and angle 1 is equal to angle 2, so I'm going to go ahead and mark those. I also know that angle 3 and angle 4 are congruent. How do I know that? They're vertical angles. Which theorem or postulate can be used that AED is similar to BEC? Well, looks like we already have two angles, so I would say angle-angle. Because they're not giving us any information about the sides, so all these three other ones need something about the sides, and this one would not be able to do that. Let's keep on moving. Number 11. Given that E is the midpoint of these CD. Oh, well, that means that CD, or CE and ED, are both congruent. And angle C is congruent to angle D. That means that this angle and this angle are congruent. Which of the following statements must be true? Well, we know that this side of angle E and this side of angle E are also congruent relationship because of vertical angles. And when we look at A compared to D, I don't think that those would match. But B and C, those wouldn't match either. CE and BE, I don't think those match either. AC and BD. AC and BD. That's saying that this third side and this third side would match. And those definitely look like they would because they're opposite this angle that's congruent in the middle. So D would have been our answer. When you look at the way that these two triangles are oriented to each other, this one on the bottom right is kind of rotated around. But you're trying to find which sides would be corresponding. And in this case, DB and AC are the corresponding sides. A right circular cone has a radius 5 inches and a height 8 inches. What is the lateral area of the cone? And they actually give us the formula here. Lateral area of the cone is pi RL, where L is the slant height. Well, if I'm trying to find the slant height here, that's actually a Pythagorean theorem relationship. I know that leg squared plus leg squared equals the hypotenuse squared. The hypotenuse in this case is L, kind of ironic since the other two things we usually call legs. And this is 5 squared plus 8 squared. That would be 25 plus 64 is going to equal that L squared. So 25 and 64 put together make 89. So the square root of 89 equals L. Why do I need to know that? Because that's in my formula here that they're giving me. They're saying that the area is going to be equal to pi times the radius times L. Well, pi is just itself, and then r in this case is 5, and L is the square root of 89. The only thing that comes close to that is D. This 39, I'm guessing that somebody like subtracted instead of added. That would be wrong. And the 445, maybe somebody actually multiplied 5 and 89. You can't multiply this 5 and 89 because they're kind of written in different terms. The square root is a function that you would have to do before multiplying. So it's kind of out of order of the operations. And the 40, I don't know where they came up with that. Oh, it looks like they just multiplied 5 times 8. That's wrong. D was the answer. If a cylindrical barrel measures 22 inches in diameter, how many inches will it roll 8 revolutions along a smooth surface? Well, let's look at a circle first. So I got a circle. And if I roll it, what's going to happen is, let's say I take a red dot here, or actually if I were to take just the eraser sign, it's as if this was going to go around the whole way on the ground though. So on the ground it's going to be rolling flat out here, but this dot is going to work its way around the outside. So it's going to start here, it's going to get there and there and there. It's going to kind of roll itself back around. And by the time it gets back to where it started, you did one full revolution around the tire. The tire went all the way around itself on the ground. So that's one revolution. So one revolution equals one circumference. Circumference. And one circumference is really 2 times pi times the radius. Well, they say that the barrel is 22 inches in diameter, so that means it's 11 in the radius. So R equals 11. So one revolution would be 2 times pi times 11, which is 22 pi. But that's not what they're asking us. They're asking us 8 revolutions. So 8 times 22 seems to be the calculation we're looking for. 8 times 2 is 16. And before, you know what's crazy? I already know the answer is C. How do I know that? It's the only one that ends in a 6. Well, then that's 16. 8 times 2 plus 1, that's 176. So it's 176 pi, because it's 8 times 22 pi. That was pretty easy. Kind of a different question, but still pretty easy. We got a sphere, a classroom globe here. It says it has a diameter 18 inches, but it seems like none of these equations actually use the diameter. They always seem to use the radius. So that radius, let's figure out how much that would be. The radius would be 18 divided by 2, which is 9. So that's our radius. And they're asking us to find the surface area, and they even give us the formula again. So the area of the surface is 4 pi r squared. And we just figured out that the radius was 9. So that's 4 times pi times 9 squared, which is 4 times pi times 81. 4 times 81 is going to be 324. Is that right? It is. But they don't do that. They actually ask us to multiply this out times pi. Well, we know that pi is actually approximately 3.14, which is really close to 3. And 3 times 32 is going to be 6 and then 9. Is that what we're looking at? Oh, that's 324. 3 times 324. Ooh, let's redo that. 3 times 324. Or to multiply this out, it should be near 1,000. 3 times 4 is 2. Carry the 1, and then we got a 7. 3 times 3 is 9. 972. But the only one even close is this one. And it makes sense that it's more than what I used because I multiplied by 3 instead of 3.14, the usual approximation for pi. I could have even ruled out the other ones because when it said 324 pi, there's no way that any of these would be close to that. So the answer had to be D. Alright, let's look at this one. It says, Vic is constructing a spherical model. And this model of the Earth for a science fair project, this model has a radius 24 inches. So we got a circle. I'm going to go ahead and draw myself a circle. And I'm going to give it a radius. And we know that that radius is 24 inches. Since roughly 75% of the Earth's surface is covered by water, he wanted to paint 75% of his model blue. To illustrate this fact, approximately how many square inches of his model will be painted blue? Well, this has got a lot going on in it. So let's first figure out the surface area of this sphere here that's got a radius 24 inches. Well, the surface area is really 4 pi r squared, like they told us in that formula, which is 4 times pi times 24 squared. And 24 squared, we got 4 times 4 is 16, 96. Then 2 times 24 is going to be 48. So put that all together, we have 576. So this is going to be 576, and we're going to multiply that times 4. Wow, 4 times 6 is 24. That's going to be 30. So 2304. So this is 2304 times pi. Well, in pi, let's just consider that to be about 3. Just do an approximation here. That would give me 12, and 3 times 3 is 9, 3 times 2 is 6. So this is about 6,912. That's a slight underestimation. So I think the surface area is actually going to be this one, B. But the question is not how much of the surface area is there. It's saying what is going to be painted blue, and which is 75% of it. And 75% is really 3/4. So 3/4 of that 7,235 is going to be smaller. And the only thing smaller than this is A. That's what you would come up with. So C and D are way too big. And B is the exact surface area of the globe. But A is only 75% of it. Last question of the section. The perimeter of 2 squares are the ratio of 4 to 9. Oh, this is interesting because we have no numbers. We just have ratios. What's the ratio between the areas? Well, okay. We know that the perimeter of 1 square. So let's figure out what this square would be. We got 1 square, and then we got another square. And if this perimeter totals 4, then this perimeter is going to equal 9. Well, then that means to find one side, I divide that by 4. So this would be 4 over 4, 4 over 4, 4 over 4, and 4 over 4. Because there's 4 equal sides. So each of these equals 1. 1 all the way around. So the area of this one is just 1. Over here, we're going to have 9 over 4, 9 over 4, 9 over 4, and so on. We're trying to figure out the area of this one. Well, that would be 9 over 4 squared, which is really 81 divided by 16. So the area of 1 square, the area of the little square, over the area of the big square, is going to be 1 over 81 over 16. And if I were to simplify that, it's kind of like 1 over a fraction. It winds up becoming 16 over 81. And the only thing that would even come close would be D. Now the shortcut to doing all this is recognizing that when you have perimeters versus the area, if we have a ratio here of A to B, the area is always going to be that squared, so A squared over B squared. And 4 squared is 16, and 9 squared is 81. That's where those numbers actually come from. And that's just kind of a shortcut that you could remember. But if you can't remember and you don't have any numbers, make up some of your own like I did. I just kept the proportions like they said to. Thank you, and see you in the next video.